To algebraically test for symmetry about the y-axis, the x-axis, or the origin, we need to conduct 3 individual tests. In this example, we have the equation y is equal to x over x squared minus 3, and we'll start by testing it for symmetry over the y-axis, which is done by plugging in negative x for every x value in the equation. When we do this, we don't make any changes to the y, but we'll open up variable holes for the x's, so that negative x can then go into those spots. And now we need to simplify, because what we're trying to determine is whether or not the resulting equation has the same collection of ordered pair solutions. Essentially, the action of replacing x's with negative x's causes the graph to flip over the y-axis. So when we flip this thing over the y-axis, is the graph going to be the same? If so, that would mean that it's symmetrical over the y-axis. So let's take a look. The parens in the numerator do not need to be carried forward in this simplify step. Because of the fact that we're squaring the x and the negative quantity, this becomes a positive x squared in the denominator. And this is about all we can do to this equation, so now we want to compare it back to the original equation. And as we can see with this negative now in the numerator, that's going to be different than the graph that we started with. So no, it's not going to have the same collection of ordered pair solutions after it's flipped over the y-axis, and therefore it's not symmetrical in that direction. Now let's test for symmetry over the x-axis. And to do that, we're going to plug in negative y for every y value in the equation. When we take this action of replacing y's with negative y's, what that does to the graph is it's going to flip the graph over the x-axis. So what we want to see here is once it's flipped, is it going to have the same collection of ordered pair solutions? Meaning, is the graph going to be the same after we flip it? That can be determined algebraically when we plug in negative y for all the y values. So we open up a hole for the y, we do not change the x's in the original equation, and we're going to plug in negative y for the y values. Now we simplify to see if algebraically the equation has the same collection of ordered pair solutions. But with the negative here on the left-hand side and no change to the right-hand side, remember we're comparing back to the original equation, this is not going to have symmetry over the x-axis. But even though it does not have symmetry over the y-axis, it does not have symmetry over the x-axis, it still could have symmetry over the origin, and we definitely need to test this. So now back up here, we see that in order to test for origin symmetry, we're going to replace not only the x with negative x, but also the y with negative y. Essentially, that means that we're flipping this graph over the x and then over the y. To determine whether or not the graph is going to be the same after both of those flips, we're going to look at it algebraically to see if the simplified version of the equation has the same collection of ordered pair solutions. So we're going to open up parentheses for all the y's, but also parentheses for the x's this time. We're going to plug negative y in for every y variable and negative x in for every x variable. Then we need to simplify and then compare it back to the original equation. So we do not need to carry these parentheses forward in that simplify step, so we'll just say the left-hand side is negative y. And the same goes for the parentheses in the numerator here. This is just going to be negative x in the top. In the denominator, notice that we are squaring not only the x but also the negative, so this is going to be positive x squared minus 3, and this is our simplified version. Now let's be careful here, because at first glance it looks like this is not the same as the original. However, notice that the left-hand side changed from positive to negative, but we also got a negative sign over here on the right-hand side, so both sides changed. Now there's a couple ways to think about this. I could actually just add this term to the left and then add this term to the right, and I would end up with the same equation that we originally started with. So yeah, it actually is the same collection of ordered pair solutions. Another way to think about that is that I can multiply both sides of any equation by a constant value, and it doesn't change the ordered pair solutions, it only changes the form of the equation. So if we multiply this by negative 1 on both sides, we see that on the left-hand side we now get positive y, and on the right-hand side we now get positive x over x squared minus 3. Now just to make sure that last step was clear, I'm going to take a little bit more space. The left-hand side multiplication, pretty simple. We've got negative y times negative 1 is definitely positive y. But to take a few more steps with the right-hand side, let's notice we have negative x over x squared minus 3, and that's multiplied by negative 1. Well, negative 1 as a fraction would be -1/1. This ratio is a negative quantity, which means that we're only multiplying the negative into the top or the numerator of the fraction. That's why it changes the sign of the x, but no change is made in the denominator of the fraction, because the negative is only multiplied into the numerator, not in the denominator. So once we multiply both sides by -1 up here, we can now clearly see that the simplified version of this equation actually is going to have the same collection of ordered pair solutions to the original, which means that we do have symmetry about the origin. Now to check our answer, let's go over to our graphing calculator and input the original equation. I'm going to select alpha and then F1 here that's in green in order to access the numerator-denominator feature in our calculator, which makes it easier to put in a fraction. So we now have then x over x squared minus 3. And when we come over here to our graph, we see the graph of this rational equation is symmetrical over the origin. And the way that we can see this is to literally take our calculator and turn it upside down. If you rotate this 180 degrees, you see that we would get the same graph that is now in the third quadrant up in the first quadrant. So this first quadrant goes down to the third quadrant goes up to the first, and the whole graph looks exactly the same upside down and right side up. And that verifies that we do have origin symmetry.